Hello everyone, myself Vidinesh and my top roll number is 536 and my topic is rethinking the design of virtual machine monitors. A virtual machine monitor is a software system that partitions a single physical machine into multiple virtual machines. Traditionally, VMMs have created a precise replica of the underlying physical machine. Truthful, True faithful emulation, VMMs support the execution of legacy guest operating systems such as Windows or Linux without modifications. However, traditional VMMs suffer from poor scalability and extensibility. There are a number of hypervisors available commercially today from VMware, Oracle, Microsoft, and Parallels, as well as those available for Linux like KVM and Zen. There are two types of hypervisors. The first type is capable of running on the bare metal without an underlying operating system of its own. The second type would run on top of a host operating system. Recovery in the OS or the VMM is very appealing. One can imagine running multiple applications, such as an editor and a playing audio in the background when one's machine crashes. When the system recovers from this error, it would be very nice to have both the editing window with unsaved changes visible and a song replayed exactly from where it was left off. This requires extensive checkpointing and recovery mechanisms in either the OS or the VMM. Commercial systems are yet to fully adapt these techniques. Operating system level virtualization allows a physical server to run multiple isolated operating system instances subject to several constraints. The instances are known as containers, virtual private servers (VPS) or virtual environments (VEs). For example, OpenVZ requires both the host and guest OS to be Linux distributions. The conditions that the software that provides the abstraction of a virtual machine or VMM must satisfy these conditions or properties are equivalence. A program running under the VMM should exhibit a predictable behavior that is essentially identical to the demonstrator when running on the underlying hardware platform directly. This is sometimes referred to as fidelity. Resource control. The VMM must be in complete control of the actual hardware resources virtualized for the operating systems at all times. This is sometimes referred to as safety. Efficiency. An overwhelming number of machine instructions must be executed without VMM intervention, or in other words, by the hardware itself. This is sometimes referred to as performance. Zen is a powerful VMM for x86, x86 64 and Titanium and Power PC's 970 architectures and follows and allows multiple OSs to run concurrently on the same physical server hardware. Zen systems are structured in which the Zen hypervisor is the lowest and most privileged layer. Above this layer comes one or the most guest OSs which the hypervisor schedules across the physical CPUs. Zen includes features such as 32 and 64-bit guest support, live migration and support for the latest processors from Intel and AMD, along with other experimental non-x86 platforms. We often hear that virtualization enhances security because a virtual machine monitor or hypervisor is considerably smaller than an operating system. For example, the Zen VMM discussed in section 5.8 has approximately 60,000 lines of code on 1 to 2 orders of magnitude fewer than a traditional operating system. A hypervisor supports stronger isolation between the VMs running under it than the isolation between processes supported by traditional operating system. Yet the hypervisor must rely on a management OS to create VMs and to transfer data in and out from a guest VM to storage devices and network interfaces. ESX server storage components. There are five main ESX server components that perform the storage operations. Virtual machine motor VMM. The VMM or hypervisor contains a layer that emulates SAS, a small computer system interface devices within a VM. The VMM provides a layer of abstraction that hides and manages the differences between physical storage and subsystems. Virtual SASI layer. The primary role of the virtual SASI layer is to manage SASI commands and intercommunication between the VMM and the virtual storage system, that is either a virtual machine file system VMFS or the network file system NFS. Virtual machine file system VMFS The VMFS is a clustered file system that leverages shared storage to allow multiple ESX hosts to read and write to the same storage simultaneously. SASA mid-layer. The main functions of SASA mid-layer are managing physical HBS on ESX server hosts, queuing requests, and handling SASI errors. In addition, this layer contains automatic rescan logical that detects changes to the logical unit number LUN mapping assigned to a ESX server host, virtual SASI HBS. In a ESX server environment, each VM uses up to 4 virtual SASI HBS. A virtual SCI HBS allows a VM access to logical SCI devices. It functions just like a physical HBA to the VM. Depending on the location of virtualization layer, there are two main hardware virtualization architectures, the bare metal type 1 and hosted type 2 architecture. In the bare metal architecture, the hypervisor installed directly on the hardware. This architecture outperforms the hosted architecture by allowing IO devices to be partitioned into virtual machines for direct access. On the other hand, the hosted architecture requires a base operating system to be installed first. The hypervisor VMM is installed on top of the hosting operating system. Hence, the is easy to install and configure on most computers without the need for customization. IO target approaches. The disk IO contention is also a problem for single server virtualization. One solution is to force the disk IO scheduling on VM and virtual machine monitor VMM levels. The selection of optical disk IO scheduler for co-located VMs can significantly improve disk IO resources. However, the trade-off between disk IO fairness and performance of co-located VMs is not very flexible and can be achieved at the cost of IO throughput and latency. Big data either require multiple disks or separate NAS devices for storage. In both cases, IO scheduling at multiple levels is required to avoid risk IO contention as a whole. So the disk IO scheduling only at VM level or VMM level will not work for big data. A VM is a software implementation of a computer that executes program like a physical machine. In formal requirements for virtualizable third generation architectures, Popek and Goldberg, who have defined conditions that may be tested to determine whether architecture can support a VM, describe it as an efficient isolated duplicate of a real machine. The fundamental concept of a VM revolves around a software application that behaves as if it were its own computer. This is the original job sharing mechanism prominent in mainframes. The VM application guest runs in its own self-contained OS and actual host machine. Put simply, a VM is a virtual computer running inside a physical computer. The virtual OS can range from a Windows environment to a Macintosh environment and is not limited to one per host machine. For example, you may have Windows XP host machine with Linux and Windows 2003 VMs. Thank you, everyone.